Ladies and gentlemen, boys and girls, welcome to another lesson from Transparent Physics. In this episode, we are going to continue our series on energy, work, and power, specifically introducing a pretty neat relationship in the Work-Energy Theorem. We'll get a little housekeeping out of the way first. As always, when you're watching the video, if you're like, oh, you know what, that makes a lot of sense, consider liking the video. If you have any questions about what I say or how I say it, please leave it in the comment field below. And to help the channel grow and to find out what's coming next from Transparent Physics, please consider subscribing to the channel. All right, in the course of this lesson, we are going to introduce what's called the Work-Energy Theorem. Notice I'm saying theorem, not theory. And we'll do a quick aside to describe the difference between what a theorem is and a theory is, often overlooked. And then we'll do a quick sample solution showing how this all comes into play. All right, there's a new equation in town. So here's the deal. We have been in this series for a while, and we just recently covered the concept of work. And way back at the start of the series on work, energy, and power, we talked about kinetic energy. Now we have an equation that combines kinetic energy and work together. It is a great equation. The work-energy theorem allows us to revisit some introductory mechanics problems in often new and easier ways. All right, then first, a quick aside on why we call it the work-energy theorem and not the work-energy theory. And these words are very easy to mix up, and I admit to making that mistake often earlier in my teaching career. We'll start with theory because we've talked about that on this channel before. And a theory is an attempt to provide the most logical explanation, in your opinion, of observed data. So you've got a set of data, and you're like, well, why am I seeing the data that I'm seeing? So you try to come up with an explanation of that. That's your theory. A theory is tentative. It could potentially be proven wrong when new data comes into play. You might even have alternative theories. Someone can look at the exact same set of data that you are and come up with a different explanation for why something's happening. And that's okay in science. The idea is that these theories compete with each other, and then new data and more research attempts to narrow down what the best explanation would be. To learn a lot more about theories and how they compare to scientific laws, I encourage you to check out the TED Ed that I wrote on that same topic. Now, on the other hand, we have theorems, and again, theorems are not exactly my expertise. They're really an extension from the world of math, and the idea is that if you start with statements that you know have been proven true, and I'm not going to debate the philosophy of like how you know something's specifically true or not, but let's just go with the argument we know certain statements are true. If we create a new statement that can be proven true using other statements that we already know to be true, then whatever that new statement is has to be true as well. True things derived from other true things are true. So a theorem is a different beast in the idea that we know it's true. It's not some tentative thing. It's not potentially going to be disproven later. A good example of this is something you might be familiar with, the Pythagorean theorem. A squared plus b squared equals c squared. This is an absolutely true statement. There are no circumstances in which it is not true, and it's been derived and proven through rigorous proofs based on foundational statements that are already true. So no one's going to come around and disprove the Pythagorean theorem. Done correctly, a theorem should be impossible to disprove because it's based on things we already know to be true. So the work-energy theorem is really a logical argument that says, hey, based on initial statements that we know to be true, we can make this derivation that we also know to be true. I am not going to go through the way in which we derive the work-energy theorem to be a true statement, but just recognize that it is an absolutely true statement that is always correct in all circumstances that we are aware of. All right, and here it is. After talking about it so much, this is the work-energy theorem. You can see the notation. We've got work next to it, the subscript net. That means the sum of all work. And specifically energy, you can see, is referring to kinetic energy. And not only that, there's the triangle in front of it. So that means change in. So we call it the work-energy theorem, but really we should call it the network change in kinetic energy theorem. But it just doesn't have that same ring, so we don't. So real quickly breaking down each side of the equation, we'll start with the work net side. Um, Work net stands again for network. Net work is the sum of all work done on an object by the forces acting on that object, and there are other videos in this series. We're talking about how you go about calculating net work. Recognizing that work is the product of force and displacement and the cosine of the angle between them. And so we solve for work number 1 and work number 2 and work number 3, etc., etc., etc. Add them all together and you get your net work. On the other side of the equation is the triangle KE, the change in kinetic energy. And this goes back a little bit into the series on work, energy, and power. Kinetic energy, if you remember, is 1/2 times mass times the square of the speed. And delta, we've talked about on and off in this channel, it means change in. So when you put that in front of a variable like that, you solve for the change in something by taking the final value minus the initial value. Expanding it all out, change in kinetic energy can be written as 1/2 mvf squared minus 1/2 mvi squared. And it's often compressed a little bit because in most circumstances, the mass of the object is not going to be changing in the problem. So since the mass is the same in both terms, we can simply combine them together, and we're left with the simpler, maybe you don't agree with it, but simpler term, 1/2 m times the quantity vf squared minus vi squared. All right, so putting this all together, the equation states that if the forces acting on an object result in a non-zero net work, and again, we've talked about how to calculate net work in an earlier lesson, the kinetic energy of the object will change. Kinetic energy involves mass and speed. So if the net work is positive, the kinetic energy of the object is going to increase, i.e. it's going to speed up. If the net work is negative, the kinetic energy of the object will decrease, i.e. it's going to slow down. And also remember, kinetic energy can never be negative. So it's just a scalar quantity. You either have it or you don't. One quick side note that might help you understand this idea a little bit better is to tie it back to something we've talked about earlier on this channel, is the idea of Newton's laws, specifically balanced forces. And when forces are balanced, that means that you have two forces of equal magnitude acting on an object but in opposite directions. And again, it could be more than two forces and they just add up so they cancel each other out, but we'll just assume it's two forces for now. When you have a scenario when there's balanced forces acting on an object and you calculate the net work, you'll see that it gives you an answer of 0 joules. Balanced forces give you a no net work scenario. Now, you could have forces balanced in, say, one direction and unbalanced in the other direction. You could have forces that are up and down that are balanced and cancel each other out. But you could have forces left and right that don't cancel each other out. So you could have a scenario where there maybe is no net work in the vertical direction, but there is net work in the horizontal direction. And when you do this, net work, if you remember calculating it, takes all the forces acting on an object and adds them together. It doesn't care that we don't do net work in the x direction and net work in the y direction. We just do net work, period. So even if you have balanced forces in one direction, you might still have a non-zero net work if the forces aren't balanced in the other direction. And when I say directions, again, I mean x direction versus y direction. Or z direction if you are super advanced at this point. Ask your teacher about the z direction. All right, this is like one of those old team-up episodes where in the comic books where Spider-Man partners up with I don't know, Iron Man to take down somebody. So we have kinetic energy and work teaming up to help us figure out how the motion of an object changes. So I'm going to hydrate myself real quick. Hopefully you're able to do the same. And we're going to move forward now with a sample solution showing you how this actually goes into effect. All right, and what's pretty much a normal Tuesday for Superman, Lex Luthor has hacked into a military network and remotely launches a Minuteman missile towards Russia. And Superman has to race to intercept it before it enters Russian airspace to avoid an international incident and starting World War III. I don't know, or maybe World War IV, depending on when you're watching this video, for posterity's sake. And so the missile has a mass of 36,000 kilograms. We're going to assume the mass is constant, even though the mass should be decreasing as the fuel is fired. The thrusters exert a constant 152 kilonewtons of force, and the missile we'll assume is just traveling at its max speed of 7,800 meters per second when Superman catches up to it. So Superman needs to bring this missile to rest within 100 kilometers. So we want to answer the question, how much force must Superman exert in order to do this? We're going to simplify the problem a little bit. We're going to ignore the downward force of gravity. There is a weight associated with the 36,000 kilograms of the missile, but we'll just assume the missile's traveling horizontally of its own power. And so Superman doesn't need to provide any vertical force to counter that. He just needs to stop it. Okay, so in a oft repeated refrain on this channel, there's more than one way to solve many problems. So we can actually have solved this entire Superman problem using a different technique, focusing instead on Newton's laws and the kinematics equations. Real quick overview, we're not going to do this on this video, but just to show you, you could solve for the acceleration that Superman needs to create in order to bring the missile to rest in the required displacement, 100 kilometers. And you could use one of the Scooby equations for that. You have enough information to do that. Once you know the acceleration, you know the mass of the rocket. Mass times acceleration gets you net force. So that tells you the overall sum of the forces that needs to exist in order for this missile to come to rest during that time, or during that displacement, maybe said more appropriately. Once you know the net force, again, ignoring anything going on in the vertical direction, you've got the thrusters pushing towards Russia. You've got Superman pushing away from Russia, and the sum of those two is the net force. And now you know two of those three things. You know the net force, and you know the force of the thrusters, so you can solve for the force from Superman. And again, could be done. Have fun doing that on your own. For now, we're going to see how the work-energy theorem works out instead. All right, then here we are. To save a little bit of time, I listed the initial information on the sheet already, but let me run through it with you guys real quick. So the idea is that Superman here is exerting a force on the rocket, and we know that the rocket is continuing to fire with a force of 152 kilonewtons. Superman has 100 kilometers to bring it to rest. Kilometers is not going to do us any good, so let's convert it to meters right now. So 100 kilometers is the equivalent of 100,000 meters. In addition, we are given the initial speed of the rocket as 7,800 meters per second. We are not specifically given the fact the final velocity is 0, but it is implied by the fact that the rocket needs to come to rest. And we're also told that the rocket has a mass of 36,000 kilograms. And then what we are interested in solving for is the amount of force that Superman needs to exert in order to bring this rocket to rest within 100 kilometers. So the equation that's going to be the basis for our solution is the work-energy theorem. So it says work net is going to equal the change in the kinetic energy. And let's get the change in kinetic energy sort of out of the way first here to the right, since we got a little extra space here anyway. So change in kinetic energy is going to equal 1/2 mvf squared minus 1/2 mvi squared. That is the final kinetic energy minus the initial kinetic energy. And we do know that the final kinetic energy is 0 because the final velocity, the final speed is 0. So when we're solving for kinetic energy, change in kinetic energy, it's just going to be basically the complete loss of whatever kinetic energy it had to start with. That'll be the change in kinetic energy. So how much kinetic energy did it have to start with? We got 36,000 kilograms, 7,800 meters per second, that quantity squared. And when you work out the math, we're going to get negative 1.10 10 to the 12th and kilogram meter squared second squared ends up giving you a value of joules. So that's the total amount of energy that we need to remove from the rocket. That goes on the right side of the problem. So everything here, this quantity is the equivalent to this over here. So we've got that already. Now we just need to focus on the left side of the equation. So work net is going to equal the sum of all the work being done, and each work is associated with forces. And we have 2 forces in play. So that's going to be our setup for work net. So we're going to see we're going to need the work done by the thruster. I'll call that WTH. And the work done by Superman, we'll call that WSU. So in order to solve for each of those, we know that work is equal to FD cosine theta. So that is the equivalent of the force of the thruster times the displacement times the cosine of the angle between the thruster force and the displacement. And then we have the force of Superman over the same displacement and the cosine of the angle between the Superman force and the displacement. So when we take a look at the picture, the displacement is to the right and the thruster force is to the right. So since they are both pointing in the same direction, that gives us a cosine of 0. The Superman force is pointing to the left and the displacement is to the right. That gives us an angle of 180 degrees. So when we solve that out, cosine of 0 just is equal to positive 1. So that's positive force of the thrust times the times displacement. And then we add that to the quantity. Cosine of 180 is negative times the quantity Superman force times the displacement. And that is all equal to the change in kinetic energy. So what we could do now is, let's get a couple more numbers in here. So the Superman force, if you remember, is our unknown. So we're going to want to solve for that in the final step. So let's get a little bit more information in here first. So the force of the thruster is 152 kilonewtons. So 152 times 10 to the 3 newtons. That's over 100,000 meters. That's minus the quantity. We're going to leave this just as an unknown for now. And then we do already have this number. I'll plug it in a second. We'll just leave it as delta KE. So when you plug all that in, make sure we can keep that separated. So 152 times 10 to the third times 100,000 meters gets us 152. We'll say 1.52 times 10 to the 10th joules. And we've got this term here. And now let's plug this guy in here as negative 1.10 to the 12 joules. All right, so we need to get that middle term by itself, and we can do a little bit of an algebraic manipulation to get that where we want it. So I can take the Superman term, I can add that to both sides, so it effectively goes to the right side. I can take the kinetic energy term, add it to both sides, then it goes to the left side. So with a little bit of algebraic manipulation, (1.1 10 to the 12 joules). So basically what this part of the equation is saying is that, hey, Superman needs to exert a force over a distance that both accounts for the fact that we need to get rid of the amount of force, or let's say the amount of energy that gets added by the thruster over that distance. And then he also needs to get rid of an amount equal to the kinetic energy that that rocket started with. So both of those amount of energies he needs to get rid of in order to bring the rocket to rest. And there we are. So let me, so if we get those terms together, it ends up, the second term, the 1.1 times 10 to the 12th, is a lot bigger than the first one, so it almost completely gets absorbed. But we'll call it 1.12. We'll just add a little bit of extra term on at the end just to show that we're adding it in there. But it almost doesn't change anything at all. The kinetic energy of the rocket is so big that the extra energy that gets added by the thruster over that last 100 kilometers is pretty much peanuts. Okay, and then we're basically ready to go. So the force that Superman needs to exert is equal to this term, 1.12 10 to the 12th. And remember, a joule is a Newton meter. And then we're dividing by D. So that's 1.12 10 to the 12th Newton meters divided by the displacement, which is 100,000 meters. So meters cancel with meters, leaves us with newtons. And when you do the math, we should end up around 1.12. We're going to go 10 to the 7th newtons. So that is that's a pretty generous amount of force that Superman needs to exert in order to bring that to rest. But, he is Superman, so. All right. And so there we go. Again, it's a different way to solve it than using, say, kinematics and the Scooby equations. In the end, is it simpler? Is it harder? That is probably up to each student's opinion, but it's not that bad of an approach, really, despite what it may look like at first blush. All right, well, that was an exciting solution. One thing before we wrap up this lesson, I want to talk about real quick the idea of net work versus overall energy change. And this is a point that sometimes causes confusion. Remember, the work-energy theorem, when it says energy, it's really talking kinetic energy. It's only change in kinetic energy. So let's say you lift an object with a constant speed. If you lift an object with a constant speed, that means the forces are balanced and there's no net work. The amount of force you're lifting up on the box with is perfectly balanced by the amount of force acting down on it by gravity, and it lifts with a constant speed. There is no change in kinetic energy. Once the box is moving, we'll assume we start the problem once the box is moving. Once it is moving, it lifts with a constant speed, so you don't speed up the box as you're lifting it higher. There is no change in kinetic energy. There is no net work, but the object's energy does change because the object's gravitational potential energy increases. So the work-energy theorem, when there's no net work, it doesn't mean that there can't be any change in energy. It just means that there won't be a change in kinetic energy. Maybe it seems like splitting hairs if this is the first time you're hearing that topic, but it's an important point to consider. All right, then real quickly to wrap this up, the work-energy theorem is another powerful tool to add to your toolkit. Make sure when you are solving it out, really it's a lot of the same things we needed to worry about when we were solving for network to begin with. Just make sure you're including all the forces acting on the object, and make sure you're getting that angle correct between the force and the displacement. You get the angle correct between the force and displacement, everything else should work out peachy keen. And as always, thanks for watching. Hopefully, I've made the concept and application of the work-energy theorem a little clearer for you on this lesson from Transparent Physics.